This is a more challenging projectile motion problem that involves multiple stages. And we're told that this test rocket is launched by accelerating it along a 200-meter incline. In fact, I'll label that now, 200 meter, at 1.25 meters per second squared, starting from rest at point A. The incline is 35.0 degrees, and we're told that at the instant the rocket leaves the incline, in fact, I'll even label that point, call it B, the engines turn off, and it is subject only to gravity. And we want to find the maximum height and the horizontal range of the rocket beyond where it starts at point A. What does the trajectory of this rocket look like? Well, it will start off here at point A. It gets accelerated uniformly along the way to point B, and then once it hits point B, it turns the engines off, and it becomes subject only to gravity, we're told. And so it should look something kind of like this. And we know that the Y maximum will be somewhere along here, and that the range is this distance right here. So let's start off with the maximum height. Part of the difficulty in this problem lies in breaking this up into stages. And in fact, I'm going to do that right here and call this stage 1, where it's being accelerated along the length of the incline, and then stage 2, where the engines have been turned off and it's just subject to gravity. So in stage 1, I want to figure out how fast the rocket is going once it reaches point B. That's something important to know, because once we know that number, we can figure out how high it reaches above point B in stage 2. And we know that there's a pretty simple kinematic equation that we can use, and it looks like this. The final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement under which that acceleration occurs. And we can simplify this a little. We were told that the rocket started from rest at point A, which means that the initial velocity is 0, and we want to solve for the final velocity. This would be at point B. So what can we do? Well, we take the square root of both sides, and we get the final velocity at point B is equal to the square root of 2 times the acceleration that happened in stage A, which is 1.25 meters per second squared. And what was the displacement under which this acceleration occurred? Well, that's the entire length of the incline, the 200 meters. So 200.0 meters. And if we put that all under the radical, what do we get in the calculator? On mine, I get the following: 22.36 meters per second. This is not the answer to part A, but rather this is the velocity once the rocket reaches point B. And now we're going to use this number to finish off part A, which happens in stage 2. in stage 2, we know that when the rocket reaches the maximum height, in the y component of the velocity, it ends up becoming 0. So what can we do here? We can end up using the same equation in stage 2, but we'll use the y component of everything and say that the final velocity squared y is equal to the initial velocity squared y plus 2 times any acceleration that occurs in the y direction times any sort of displacement that occurs in the y direction. And what is this quantity here? Well, delta y is just the height that the rocket reaches above point B. And why do we care about that? Well, we know that y maximum is going to be equal to the height of the incline, which is 200 sine 35 degrees, plus whatever extra height the rocket reaches in attaining the maximum height, so delta y. So if we can figure out what delta y is, that's the answer to part A right there. So let's go back to this and solve for delta y. In stage 2, when the rocket reaches the maximum height, the final velocity will be 0. Okay? So this is 0. That makes things easy. And the y component of our initial velocity is equal to what? 22.36 meters per second, but the y component, so sine 35 degrees, plus 2 times negative 9.8 meters per second squared, delta y. Since we have a 0 on the left-hand side, we can move this whole quantity over to the left and easily solve. So let's go ahead and do that. We take delta y is equal to 22.36 sine 35 degrees divided by 2 times 9.8 meters per second squared. And if I keep the units up here, this would be meters per second. And what is delta y when we solve for this? Let's not forget the squared. Squared. Well, we get 8.4 meters. So 200 plus, 200 sine 35 plus 8.4 meters is equal to what? Well, I get 123.1 meters, and we need to report this answer, the maximum height that the rocket reaches, to the smallest number of significant figures that we were given in the problem description. So here I see 4, here I see 3, here I see 3, which means we need to report it to the smallest number, which is 3. So looking at our answer here, 123.1, 1, 2, 3 significant figures. The cutoff is right here. The 0.1 is smaller than 0.5. We don't round up, we actually round down. So I use this symbol here, approximately equal to 123 meters. That is the answer to part A. The maximum height above the ground that the rocket reaches is 123 meters, rounded appropriately. So what about part B? The greatest horizontal range. So we'll do the similar type of approach, but this one involves a different equation. And in fact, it looks like this. The final position is equal to the initial position plus any type of velocity that you're using. In fact, this will all be in the y, so I'm going to put y subscripts on everything. y times t plus 1/2 acceleration in the y direction times t squared. So what is the approach here? Why are we using this equation? Here's what the plan is. We know that part of the range is the horizontal piece of the inclined plane that the rocket had to travel on in stage 1. And this would be 200 cosine 35 degrees. So we know the range is equal to that plus whatever distance the rocket traversed while it was in the air. We'll call this x, or excuse me, we'll call this the initial at point B times the amount of time that it was in the air. So we already know part of the range. This is just a number. That's pretty easy. We know what the initial velocity was at point B, but we don't know the amount of time that it was in the air. And hence, we're going to use this equation to solve for the time that it took to get from point B down to the ground. And so the final position, using this equation here, in stage 2, the final position, excuse me, the final position is down on the ground. It's down at y is equal to 0. What's the initial position? Well, that's up here, that's this distance. The vertical portion of the inclined plane, 200 sine 35 degrees, plus the y component of the velocity at point B, which is what? 22.36. But the y component, so sine 35 degrees, and that's like meters per second, times a time, which we don't know. And we know that in stage 2, the acceleration that the rocket is experiencing is due to gravity. So the last piece of our equation here, we can say minus 1/2 gt squared. I'll kind of separate this here. So here's our expression. And notice, this is a quadratic equation. We've got a t squared here, a t here, and some constant number equal to 0. So what does that mean? We're going to have to use the quadratic formula. And don't get it confused. The a portion is attached to the t squared, not this initial constant part here. So a is minus 1/2 times g. B is equal to what? 22 0.36 sine of 35 degrees, and C is the constant portion, 200 sine 35 degrees. Okay, we can kind of color code that like this here. Blue here, and then the red right here. And what are we going to do with this? ABC. What are we trying to figure out? Well, we're trying to figure out time. So that means time is equal to, how does the quadratic formula go? I believe it's minus b plus or minus the square root of b squared minus 4ac all over 2a. And I'm not going to plug all this in here. It's pretty easy to do. If you solve this correctly, you will end up with 2 times. One will be positive, and it should look like this value, 6.32 seconds. The other time is negative, and it doesn't make sense that it would take a negative amount of time for the rocket to go from point B down to the ground. That doesn't make any physical sense in this context. So we don't care about that number. We just throw it away. And we keep this one, 6.32. So it takes 6.32 seconds to go from point B to ground. And that means that we are plugging 6.32 into this expression right here. That's the t that we want. That's the time. And let me move that out of the way. And this will be 6.32 seconds. And we know that the initial velocity at point B, that was solved a long time ago, 22 point, we have to use the x component, pardon me, 36. We have to use cosine of 35 degrees multiplied by this 6.32. And what happens when you add this plus this multiplied by that? Well, we get 279.6 meters, around there. And remember, just like in part A, we need to truncate to 3 significant figures. So here's 1, 2, 3. Cutoff is right there. A 6 is above a 5, so we'll round up. And our answer for part B is 280 meters. And just to recap, what did we do? Well, we already knew that for the range, we had a partial answer already, the horizontal component of the inclined plane. And then we said that, hey, we can figure out the horizontal portion of the trajectory after point B if we use this equation here, and we figure out how much time it takes to get from point B down to the ground. And we did the quadratic formula, and we found that there's a positive time that makes sense, and we took that as our answer, 6.32, and we said, hey, the range is equal to the x component of the ramp that it went up plus this piece here. And so if I kind of color code these, this is the green and this is the red. And when we add them together, we get 280 meters. That's it for part A and part B. Thanks for watching.